Okay, the next part we will compare different basic stages. We compare the noise performance of basic amplifying stages, and then we have the three alternatives that we discussed previously. We have the first the common source stage, and then remember that the common source stage looks like this. Okay, so they look like this. The common drain stage looks like this. And the common gate stage looks like this. And when we studied the common source stage, we had that the stage has the largest amplifying capabilities. So the parameters A, B, C, and D were very small for this stage. So the common source stage is the best alternative from the noise point of view, because when we refer the output noise current to the input, it has to pass through these very good amplifying parameters, and then it will result in a small input refer noise. If we take the common drain, for instance, we have that the common drain stage has one parameter that is equal to 1, and the common gate also has one parameter. So in the common drain, it is the voltage gain is approximately equal to 1, whereas in the common gate is the current gain that is approximately equal to 1. And then when we refer noise sources from the output to the input, they will have lower performance than the common source stage. Yeah, so the other parameters are more or less the same. But in some situations, the common drain and common gate are not going to perform very well from the noise point of view. So we have to be careful when we use common drain and common gates. It is not that we cannot use them, we can use them, but they will not provide the same noise performance that the common source stage. In balance configurations, for instance, in differential pairs, the analysis that we're going to do, it is very similar to the analysis that we have done for the single-ended amplifier by basic configurations. And for instance, for the differential pair, we have two transistors that are the same size with the same bias conditions, and when we connect them, both of them will have their input refer noise, as we see here. Now to get a total input refer noise, because that is what we are after. We are after a model that comprises the complete balance configuration. We can call it this VN total, and current source EN total here. So what we can do here, it is to first when we see these noise sources, we can conclude almost directly that the input refer voltage of the stage on the top and the input refer noise voltage of the stage in the bottom are in series. They are going to be in series to a source, so we don't need to do anything for these two. They are already in series. But the current, on the other hand, the current sources, we need to work on these ones. And what do? We move this current to the output. We move also this current to the output. We move it, and we move it by using the C parameter, that is the transimpedance, converting a current to a voltage source. So when we do that, we have at the noise current from the input has been converted in a output voltage. The position of the the plus in the voltage source is important to keep the sign. We do the same for the bottom stage. And then we have this noise voltage here. And then we can reuse things that we have already learned from the differential pair in previous lectures. A differential pair formed by the two-port networks ABCD becomes a two-port network in which the voltage gain is the same, the transconductance gain is half, the transimpedance gain is twice as big, and the current gain is exactly the same. Now these two voltages are in series with the output, so this is in series with the output voltage. So we can pile them together, like we do here. And then we can move this output voltage towards the input by using the transimpedance again. So when we move it at the input, what we have is the following model for the differential pair. So we have that the input referred noise voltage in a differential pair is equal to the noise of the one of the stages plus the input referred noise of the other stage. If they are the same, when we square these ones, will be Vn1 square plus Vn2 square. They are totally uncorrelated, they are different transistors, but if they are biased with the same current and they are exactly the same size, then this will be equal to 2 times the noise of one block. Then when we check the noise currents, on the other hand, we see that we have the noise current 1 is divided by 2. We will square this one plus the En2 divided by 2 square, and then we will have In1 square divided by 4 plus In2 square divided by 4. And again, both transistors, both devices are biased at the same current and they are exactly the same size. Then this will be equal to N square divided by 2. That is very nice because then we can see directly that the input referred noise of a differential pair can be characterized by the input referred noise of a single device quite easily. We can also write it like this. That is very useful when we do our scripts for noise calculations. Okay, so this is what we can say about the input noise in differential pairs. Anti-parallel stage, when we connect the devices, for instance, in parallel, a very easy example, it is an inverter amplifier. We do similar treatment as we did for the differential pair, and then what we have is actually the following results. So we'll take the result here. In this particular case, when we put this configuration in anti-parallel, what we have it is that it is the voltage, the input referred noise voltage, that it is average, and it is the input noise current that it is added. So it is the opposite that in the differential pair. Okay, so we have handled the differential pairs, the anti-series stage, and in the anti-parallel stages that are more or less the ones that are common in analog integrated circuit design. So those are the ones that we are going to use more. Now we talk a little about that we need to move these noise sources toward the input source so that we can do a signal to noise calculation directly at the input. And typically what we will have is that our amplifiers, or at least the input stage of our amplifier, will look something like this. For instance, if it is only one transistor, we have already seen how we can obtain the input referred noise voltage and input referred noise current. When this amplifying stage is connected towards the source, and the source can be a voltage source, for instance, it can be also current, it might be that there are other impedances around, and then we have to do some movement of these noise sources. And because what we are after is that we want to find a total input referred noise source that it is in series to our source, because here when we have our signal here and then our noise, total noise here, then we can do the calculation of signal to noise ratio and do comparisons of different amplifiers that have different input referred noise. So we want to find this total input referred noise voltage in this particular case. And the tools that we will use for that are basic tools that most probably we study in the basic electrical principle courses. And the first tool it is the Thevenin to Norton transformation. So when we have voltage source in series with an impedance, we can convert it to a current source in parallel to the same impedance. And for the conversion, the current source will be equal to the voltage source divided by the impedance. Then we have also the following tool. We have a current source that is connected between nodes B and A. This current source can also be represented as a current source that is connected between B and C, and another current source between C and A. Okay, so and vice versa. These two current sources can be represented by A, B to C, and C to A can be represented by a current source from B to A. And the last one is that we can push voltage sources. So we have, for instance, this crossroad, this node that it is represents a crossroad. We can push this voltage source, and then this voltage source is equivalent to having 3 voltage sources after they cross this node here. Okay, so these are the basic tools that we are going to use for moving noise sources, and actually they are exactly the same tools that we are going to use later for biasing, to move current and voltage sources for biasing. Okay, so we'll have our first example. We have our 2-port model with the input referred noise voltage and noise current. When we have these ones, we can already forget about the 2-port model here, because now we are just going to start moving these sources in this direction. Okay, so the tool that we're going to use first, it is that we're going to push this voltage source in this direction and in this direction, and then we will have it is the schematic that it is in picture number 2. Okay, so very important for this to work, we need to keep the signs. So when we push this voltage source, we will have our voltage source with the plus here and the plus here. Now the next step, we're going to basically we are going to move this one in this direction. So It is already in series with the source, but there is nothing else we need to do for this voltage with this voltage source. The next one, it is we are going to convert this impedance and this voltage source into a Norton equivalent. So we divide this voltage by the impedance, and then we get this current source here. And now we can add these two current sources. We add these two current sources here. And then the almost last step is that this current source here and this impedance here, they can be converted in a Thevenin equivalent. Okay, they can be converted in a Thevenin equivalent. So again, very important to keep the signs. This voltage is going to be produced on this impedance is going to be plus minus, so the voltage source has to be plus in this direction. So when we find this voltage source, then we have basically all the voltage sources that form the total input voltage referred noise already in series with the source, and we can calculate the total input referred voltage noise here. Notice again, these impedances might be complex impedances. We have complex impedances here and here. We know that IN and VN are also complex numbers, 90 degrees phase shift. Then when we do this complex multiplication, then we will get other complex numbers, and then when we square, they are going to give us basically the power density, the total power density. It is very important to keep in mind that these complex multiplications are done on correlated noise sources. If we don't take in consideration the correlation, then we will arrive to a wrong result. We will see that in our example. So here we have a typical example. We have our amplifier that can be defined with ABCD parameters. It has an input referred voltage noise. This noise, it is typically coming from the first transistor. We are going to assume that our first transistor, it is a common source, which is a very good assumption. Typically we want, as we explained before, to use common source amplifiers first stages because of the lower input referred noise. And then we have an inductor, and then we have a voltage source that includes a series resistance. So this is a very typical case. Input voltage in company of a source resistance. The source resistance will produce thermal noise. So let's try to do some input referred noise calculations here, and then we see almost directly this is in series, so I can already move this one towards the input. There is nothing I need to do with this voltage source. The noise of the source resistance is also in series, so I can move it directly towards the source. There is nothing I need to do. The only one that I need to work with, it is the input referred noise current, and in order to convert this one to a voltage source in series, I need to multiply by the impedances here. So when I multiply this current source by the impedance, then I get the following model. So we get Vn that was in series, VRS that is in series, and En that gets multiplied by all the impedance that is in series, that it is Rs plus G omega L. Then if I assume that I have one transistor here, and this transistor has Vn and then has En as input refer noise, and En is equal to Vn multiplied by G omega C. Then I just replace this one here, and then we start to see how important it is to keep the signs and what is the impact of multiplying complex numbers with complex noise represented by complex vectors. We just go a little faster with the math. We get the following expression for the total input refer noise voltage, and at this point I have a real part that it is here and here. I have an imaginary part that's here, and this is also going to be real. Then I can square it here, and then when I square it, I get a Vn squared here, the real part squared, the imaginary part squared, and then this is coming from the resistor. I replace the equations for the different parts, and then I get Vn squared is here, and then for KTRS is here. Okay, so then we have some terms that depend on omega square here, and then we have terms that depend on F, and don't forget that omega is equal to 2pf, so we can actually change this one to omega C omega, or the omegas here to 2pf, but typically we keep it the equation as here, as it is. So we have it the following equation, and yeah, when we have this equation, we can do many interesting things, but first we have to check that our equation is actually giving us the result that we expect. So if we use the same NMOS transistor that we used before for the extraction of input refer noise voltage and noise current, and then we put the source resistance of 500 ohms and these inductors of 2 microhenry, I use these equations to put it in MATLAB, and then I get the following plot. I get the following plot in MATLAB, and then I run the same let's say circuit in Cadence, and I'm going to show you the simulation setup very soon. Then I get the following plot. Now we can check first that actually the equation it is giving me a valid result. We take for instance the thermal noise, the white noise, and then we get around 7.8 nanovolt. The simulator tell me that it is around 6.1 nanovolt. We get the flicker noise at 1 kilohertz, it is 36 nanos. We get the 34 nanos here. And then something very interesting, we have this part here. It is 1 minus omega square LC. This factor is minimized when omega square LC is equal to 1. So when omega is equal to square is equal to LC, or omega is equal to square root of 1 over LC. So at this particular frequency, this part it is going to be minimized. And then we can see it. Our equation captures this part, this frequency that is minimized. It is located here, and then also Cadence tells us that point here. If you don't keep the correlation and you just take the noise power levels, you will miss, for instance, this will not exist in your equation. Then we get another part, the part that grows very quickly with frequency. You will get some part that grows with the square of the frequency, and depends on the total capacitance and the series. So that you grows like this, it grows like this here, with the similar levels as we simulated. Okay, so let's take a look very quickly to the simulation setup of this example. We'll have it. So this is our simulation setup, and then basically what we do is exactly the same. We go to the EDXL, and notice that the simulations for the input referred noise can be quite simple. I have the transistor already biased with the self-biased transistor that we have discussed before. So it has the current, the VDS, and the gate source voltage that I calculated and I extracted using the material from the Electron devices. And then what I do is I just run DC operating point and a noise simulation, and basically it's the same setup of noise that we run before. For the DC, I am just running an operating point and saving the operating point. So very quickly, let's run the simulation. Then when we run the simulation, we put this one in log scale, and then we can find all this all the information that we describe in our equation with exactly the same parameters. Take a look to the DC operating point just to make sure that our transistor is exactly biased where we want it to be biased. So let's check the noise voltages there. So it is a 900 millivolts, and the current DC operating point, and then we have 10 microamps. So it is biased at 10 microamps, VDS 900 millivolts. Okay, very good. So we can continue. Okay, so we have different impedance feedback configurations that we studied in the previous lecture. We have a voltage amplifier, we have a transconductance amplifier, transimpedance amplifier, and we have a current amplifier configuration with passive feedback components that they are pretty much used, and they are the basic stages that we use. And now we are going to do is to find suitable models for these blocks, and then we start with the voltage amplifier. So we have the voltage amplifier, or voltage amplifier. If we put all the noise sources, we assume that we are using resistors in the feedback as a feedback components, then each resistor will have thermal noise. And then we have, for our amplifier itself, we will have the input noise current and input noise voltage. So we start from this point, and then from this point, what we do is that we will start working with this current source. So this current source can be split in two current sources: a current source that take current from this node here, that it is exactly the same as here, takes the same amount of current EN towards ground, and then from ground, same current coming up to the positive input of the amplifier. So we have used this duality of the current that we explained before. Now what we can do here is that we can convert this resistor and current source in parallel to a voltage source in series, so a Thevenin equivalent. So when we do that, and we are careful with the with the sign, this current is going to flow in this direction like this, and it's going to produce voltage fall in this direction, so it will be facing down the plus of the voltage source. So we have added this voltage source here, and then we have done step 2 and step 3. Now we can do is we have a total voltage source here. We're going to start moving this one in these directions. Okay, so when we push this voltage source, when we push it, remember that the voltage difference here is 0 volts, so we deal with these two nodes as if they were at the same potential level, also as they were a short circuit. So when we move this voltage source in this direction, it ends up with a plus here as it is now, and the other moves in this direction with a plus here. So this is a step 4. Yes, it is a step 4. Now I'm going to move this total voltage source in this direction and in the direction of the output here. Now, and then we end up with this schematic here, and yeah, now we notice, and here it is very important, that the feedback itself will guarantee that this voltage source will be swallowed by the amplifier. So it is very low output impedance in this nuller, and basically it will correct for all this voltage that exists here. So we consider that this one is going to be eliminated by the feedback, by the infinite gain of this amplifier and extreme low output impedance. So output voltage will not really depend on this one. Yeah, but on the other hand, there will be this one here. We will have this remaining output voltage here, and then what we can do now it is to move this one towards the input, and then for that we're going to remember that this block has a voltage gain equal to R1 plus R2 divided by R1. So when we divide this voltage at the output by this gain, then we will get an input refer noise voltage. Okay, so and that is what we do. That is what we do here. Important to keep the sign. The sign was here. The sign will also be here. Okay, so we have basically all the noise input refer noise voltage in series, and also we have the current source, noise current source, that it is basically ready. So when we expand the terms that depends on V1 and V2, so what we get it is the following. We get the following expressions here. And then now we can analyze a little bit these ones. So when we take only these two, we take only this one, and we squared this one, we will get the following equations. And for V1, remember that V1 square is equal to 4kT R1, and V2 square is equal to 4kT R2. So when we replace these ones and do a little bit the math, we have the following. We get the following expression for these two parts of the equation. Then for KT, R1 R2 divided by R1 plus R2, and this is like having these two resistors in parallel. Yeah, so the total noise squared, the input refer noise spectral density, it is equivalent to having these two resistors in parallel. So this one we will call V12. Now when we see the noise current also, we come back here, we see that the noise current also appears to be multiplied, but also by R1 in parallel to R2. So based on these observations, we can build the following input refers noise model for the voltage amplifier. So for the voltage amplifier, we have that the input refer noise voltage of the amplifier itself can be moved directly to the input, and then we have these feedback resistors R1 and R2 in parallel, producing this input refer noise voltage. And then we have the noise current facing up, that it is also going to get multiplied by R1 and R2. And this is going to be the model for our voltage amplifier. So every time that we have something like this, R1, R2, then we can use the following noise model for this one, which is very handy. We don't need to do all this moving of noise sources every time. So we can use this noise model. And precisely as we did for this device, for this amplifier, we can also find suitable models for the other amplifying configurations. So in general, I mean, we did the calculation assuming resistors R1 and R2, but they can be impedances, complex impedances, and we have complex impedances. The model is going to be the same. What it changes is that the input refer noise power density will depend on the real part of zeta 1 in parallel to zeta 2. So those are the ones that produce thermal noise, the real parts, the resistive parts. For the transimpedance amplifier, we remember the transimpedance amplifier looks like this. So we take the output voltage here, and then we have zeta 1 here, and then we will connect our source here. So the model, the noise model for this amplifying configuration is the following: input refer noise of the amplifier itself here, and then we have the feedback impedance also connected here, basically in parallel to the source, and then the noise of the feedback impedance also in parallel. Okay, so just for completeness, remember that something that I talked before regarding that we make some mistake when we extract the input refer noise current, and we see that the resistor here behaves like a transimpedance amplifier, and if we go to our model here down, whenever we will need to move this input refer voltage noise towards the current, So to move this one to a current, we will need to divide it by zeta 1, and then Bn divided by zeta 1, and Bn contains 1 over F noise and thermal white thermal noise. So zeta 1 will introduce 1 over F noise in our input, total input referred noise current. So that is the reason that we saw some 1 over F noise in that simulation setup. Okay, if you were wondering, it comes because of this, because we use a similar configuration to be able to bias that transistor. For the current amplifier looks like this. We have this terminal, it is like this, and then we have a current source here, and then we have like this, and then the output current it is here. Okay, so then our output current is going to be here. So we have this situation here, R1 and R2. The model for this one is the following. So this there will be impedances zeta 1 and zeta 2. These impedances are in series, and then we get the current of this series impedances will be here, zeta 1 plus zeta 2, and then we will have the input referred noise of the amplifier itself. And then we have exactly the same situation as we saw before. This will be connected to the source that it is here, that probably comes with its impedance, and whenever we divide Bn by this impedance, then we will have also some 1 over F noise that it is going to appear. Okay. Then finally we have the plus minus minus plus. We have the transconductance amplifier. And this is going to be connected to a voltage source. Then the model for this one, it is the following. Okay, so we have the input referred voltage and noise current of the amplifier itself, and then this resistance here appears in series, and all the noise of this resistance also appears in series naturally. So then it's important to remember every time that we put a resistance here, all the noise will appear in series. So this is one of the characteristics of this stage. It's easy to calculate the noise for the transconductance amplifier. Okay, so the last thing that we're going to do is we're going to do an example of noise optimization. And for that example, I will have a voltage amplifier, and then for this voltage amplifier, we are going to assume that we have a voltage gain of 10 or 20 dBs, and that this series resistance is going to be equal to 1 kilo ohm, and that we are interested in a bandwidth of 1 kilohertz to 1 megahertz. Okay, so we're going to work on this example.